states which are inserted on the inputs of these Riemann surfaces and which were elements of this conformal field theory. And what I do is I simply expand them. Now remember, in this world sheet theory, we had the embedding coordinates. These were the sigma model fields, but we also had ghosts. And the ghosts have a degree and parity. So we simply expand the C and the B ghosts. They are odd. They are parity odd. So they can at most appear linearly, if you wish. But at the same time, they live on the circle. So they have an infinite number of Fourier modes. So there's still infinite number of Fourier modes along this circle. So these are still, as functions, is still an infinite dimensional vector space. So now I can simply expand this psi in terms of these powers of B and C. And the coefficient function, and also in powers of these derivatives of these embedding coordinates. These are the quantum fields of the auxiliary quantum field theory, which form this PRSD algebra of the auxiliary quantum field. And the coefficient functions in front, they may depend on just space-time coordinates. These are the space-time fields. So there could be a graviton, which is a symmetric tensor, which can contract with this phi. There can be an antisymmetric tensor. That's what we call a Kalb-Ramond field. There can be a scalar, which contracts with just the inner product. There's the dilaton, and there can be more. There are many, many more fields, but just to give an example. But at the same time, all these fields are parity even, because everything in this bracket this far is all parity even. But then you can also have a B times something. So this is parity odd. So therefore, this should be a ghost. And so this epsilon phi is a space-time ghost, which is the space-time diffeomorphism, for instance, is in there, or gauge transformation. So the point I want to bring home here is simply that when you follow this route, you cannot avoid it, but you will get a full BV theory. And with the full BV multiplet, you don't have to extend it. It's just there from the very beginning. Right? It just comes with just the expansion in this ghost sector of this auxiliary quantum field theory. The coefficients of this expansion in the ghost sector of the auxiliary quantum field theory is the whole BV multiplet of the space-time theory. So there's this pairing. So you have automatically get a complete space-time BV multiplet. So that is one important property of this construction. And as I said, these vertices that we've written above, or these Fn's or the Ln's, they are the vertices of this perturbative action, perturbative expansion of the action in space-time. So finally, the form of the action which you get looks like this. So we have this inner product, and then you get psi cube psi. Psi is this PRSD operator of this Faddeev-Popov quantized worldsheet theory, auxiliary theory. And then you get this. That's the cubic. This comes from a Riemann surface, the cubic vertex, and then with quartic vertex and so on. So these are now the vertices of the space-time theory. So it looks like that's how the space-time theory looks, but typically we'll have an infinite expansion. So it'll be non-polynomial. Level matching, yeah. So this is already is implicit. So I'm a bit sketchy here. I'm not. Yeah. Oh, so it's just the worldsheet parity. So here it's just, I take the total parity, but this would be the worldsheet parity. And I take the total parity to be the worldsheet parity plus space.
There are many kinds of parities. Which parity?
Oh, I see. Just so the what do you call it? The Grassmann parity.
Yeah. Grassmann? Okay.
Grassmann parity.
Okay.
Yeah.
Thank you.
Sorry. Yeah. Thank you. So note also that the action looks like it's a Chern-Simons type action. It's psi cube psi. It's not like something like it looks from the distance like should be more like a Chern-Simons type theory like we saw yesterday in Christian Seeman's talk. But that's misleading because this Q actually also has second derivatives in space-time. This operator Q, although it's nilpotent, it involves also second derivative. So in particular, you could write the phi box phi theory. You could simply write it in this form by defining an object to extend the inner product by having also not just integration over d4x, but also over some odd, parity odd, Grassmann parity odd object, dc. And then you simply multiply this box with C, and this is what you would define. And I think that's also something that Yuji uses a lot in his description of correlation function quantum field theory. So any quantum field theory, and Yuji said this yesterday, can be formulated as a BV theory. Even if you have no symmetries, even if you have no gauge redundancy, you can still formulate as a BV theory by this simple trick. Of course, it doesn't necessarily buy you very much. Sometimes it does, but it can certainly be done. That this chain map property is fulfilled, that in fact there is a BRST operator in this theory, that this has these redundancies, is I need to assume I need to make certain assumptions about the target space. So this takes values in this target space. This target space can have extra structure, can have a metric, can have other structure. I made to make certain assumptions on this the target space metric in order for this to really be a chain map. So that means the theory becomes background dependent because I need to make choices here. Otherwise, I cannot do this last step. So everything that's geometric is completely background independent, but this last step, which is this vertical arrow, is actually background dependent. This then raises the question about, is this whole formulation actually background dependent or not? So had I chosen another background and I would do an expansion around the other background, would I get the same theory or would I get something completely different theory? And there was old papers by Zwiebach and Sen where they discussed background independence. So here, if you formulate this in terms of these homotopy algebras, what you will say is, suppose I have a certain target space background, then I do this whole program, and as we saw, at the bottom corner of this triangle, there will be the endomorphism, there will be an L-infinity algebra. So I'll denote it by L. Now suppose I want to deform this L-infinity algebra. I want to take a different L-infinity algebra. So how do I even check if it's different or just a rewriting of the same? So for this, you use the deformation theory. And so it's a cohomological problem. So what you do is you take the Chevalier-Eilenberg. It's like deformations of Lie algebras. Take a Lie algebra and you want to know what is a proper deformation of a Lie algebra. Is you write like this. So you have this bracket. And this is the Chevalier-Eilenberg differential. So the cohomology of this differential, these are the inequivalent L-infinity algebras. So inequivalent, where equivalence classes are just L-infinity isomorphism. So now what you can do is you can consider the class of Polyakov actions, this auxiliary quantum field theory. You can say, well, let me deform it a little bit. Let me try to take another. But I assume that, for instance, change the background a little bit, change the target space background a little bit. But I assume that the worldsheet fields are still the same. These BRST worldsheet fields are still given by phi, B, and C. So then you can show that in the closed string, this cohomology is actually empty. So there are no infinitesimal deformations. So therefore, closed string field theory is at least locally unique. Now, of course, you do not know that maybe there's another background which is not continuously connected to the one I already had, where maybe target space has a different dimension, maybe is a completely different object. It's also consistent, but it's not continuously connected. Then this no longer works because then it's not an infinitesimal deformation of the given theory. So probably string theory has many solutions. Some of them don't correspond to space-time at all, completely different. Maybe matrices like Kepler models. They're probably not continuously connected to them, and I don't know. I cannot make any statements about this. So So that is the statement of background independence for closed string field theory. In open string field theory, situation is a little bit different. You can also run this program, and what you find is that there is a deformation, there's a non-trivial deformation of closed open string theory. So there's one open string field theory, there's another open string field theory, and another. They're really different, but you can show that the cohomology of this deformation, Chevalier-Eilenberg, or Hochschild in that case, is actually the same as the closed string cohomology. So the only way to deform an open string theory is by inserting a closed string in the bulk somewhere. So you turn, like that's basically the statement of you can deform Yang-Mills theory by coupling it to gravity, putting in a non-trivial gravitational background. And we know that, right? Yang-Mills theory is a very good gauge theory in any geometric background, in any metric background. It's always a good gauge theory. But they are different, right? So the actions are really different. So in string conditions a bit stronger, in order for the gauge symmetry to be preserved, Yang-Mills theory, in quotation marks, preserved, the closed string background or the gravity would have to be on shell, would have to satisfy Einstein equation. So open string field theory actually also knows something about the closed string. And this is something I think that is somehow surely related to ADS-CFT correspondence. I know Yuji and many others are thinking about this, and I think there's an interesting story ahead, but it's still not fully answered. Please.
Sorry. How is this related to the proof of background data? That
In sense, for background, very closely related, they take a field theory, a string field theory where you have a given Q, and then you take a solution, you shift Q by this solution. And then you just see what are the properties, if you know, how, so it's how to say, it's in a way equivalent, I think, except that it's you work directly on the level of conformal field theory, just what happens. So you never violate the conformal symmetry. But it's surely equivalent in some sense, although background independence and uniqueness, there is a little bit of extra work to do. One has to really do this Hochschild deformation or the Hochschild cohomology. So that is what you need to do. Yeah. Okay, so now the thing is, so far, as I said at the end of yesterday's seminar, is that
yeah. Can I?
Yeah.
In the previous slide, I missed the punchline. So for the closed string, are you saying that it's impossible to deform target theory without modifying worldsheet?
No, even when you can even modify the worldsheet, but if you modify the worldsheet in a way that preserves the same BRST field, so you don't add any new fields here, then it's still a trivial deformation. So it can be, it's just a field definition.
Okay, and then for open strings, you can modify target theory without changing the worldsheet.
You have to change still the worldsheet, but the worldsheet gets modified. So what happens basically, you can modify this G in an open string, and that corresponds to a closed string data.
Okay.
So still the set of worldsheet fields stays the same, but now this deformation of G is a G-Neumann moduli. Whereas in closed string theory, this deformation of G is just an excitation.
Okay. Yeah, thanks.
In the closed string, locally trivial. Yeah, in the closed string. Yeah. As I said at the end of yesterday, so far, okay, except for this uniqueness part, I've not done anything new. I've just identified an L-infinity structure in an existing framework that was already there for many years. So now we want to actually use it. We want to turn things around and say we want to actually use the A infinity or L infinity structure to get something new. And so this is indeed the case for superstring field theory, because in superstring field theory, what's the difference between string field theory and superstring field theory is that if string field theory was based, or string theory rather, was based on a Riemann surface, this, so, and we were studying the moduli space of these Riemann surfaces, maybe of genus G. In superstring theory is based on super Riemann surfaces. So that means if I have a coordinate here, so locally I can parameterize by, okay, too big, but I can map this into some local neighborhoods of the complex plane, and then with some coordinate Z, and being a Riemann surface, and we know that the transition functions between these two coordinate patches will be holomorphic. So now a super Riemann surface means that you add a second coordinate. You have an odd coordinate. You need also an odd coordinate to parameterize this. And then the transition functions between two coordinate shots, they will have not to be conformal, so not holomorphic, but superconformal, which means basically supersymmetric. So this is, as a geometry, this is complicated in a way, no? Because it's not so clear what is geometries of odd variables. So this is really where we enter the realm of algebraic geometry. This is really defined in terms of functions on this object. So, and the price we pay is that we don't really have a geometric notion of this, is we will have problems with this geometric boundary BB equations. But let's just explain a little bit more first the setting. So instead of a Riemann surface, we consider super Riemann surfaces, so which are locally look like a complex plane with an even and an odd coordinate locally. And you need to have what's called a rank 0, 1, so an odd subbundle, which is basically a covariant, supersymmetry covariant derivative. It's a d theta plus theta dz. So this is a typical section of this tangent bundle of this super Riemann surface, and it should be maximally non-integrable. That means that if you take the square of this, it should not be proportional to itself. So that is what you assume. So that's the analog condition of having a Riemann surface. A super Riemann surface is a superspace. So with two types of coordinates, with this extra condition that there is a global section that is nowhere, that is maximally non-integrable, so it never squares into itself. So that's the setting. Now let's take, for instance, an open string. So again, I replace this by intervals. So then it's an open string, and then we can have punctures. Again, just like before. And I take genus equals 0, so I assume just for simplicity. So then we don't have extra dimensions in the moduli space. Then what we do is we can ask what is the moduli space of this type of Riemann surfaces. So it depends on the number of punctures. Like in the bosonic case, the more punctures I have, if I have more than 3 punctures, then there is always at least one modulus. So that happens here too, right? So there's this -3. But there are also the questions, what happens in the odd directions? So in the odd directions, what do you even mean by a puncture here? So the idea is, the way I try to describe it, the black part would be like the bosonic part of the Riemann surface, so the reduced part. And then I have this bundle on it. And the yellow part is this open bit, or open, which is this odd coordinate, described locally by this odd coordinate, theta. So in this yellow stripe, I can either have a puncture, I can either have a point. If I have a point in this yellow stripe, we call this a Neuve-Schwarz puncture. Or you can have a situation where this non-integrability somehow collapses, where D actually does square to itself. So that's a singularity. And then we call it a Ramon puncture. So these are the two types of punctures we can have. Both are important in string theory. So we need to consider not just a bosonic puncture, but also a Riemann puncture. An easy way to make a Riemann puncture is you take a Riemann surface locally equivalent to Z, and you replace Z by square root of Z. So you take a double cover of the neighborhood around Z equals 0, and then this Neuburg-Schwarz puncture becomes a Riemann puncture, loosely speaking. So if you do something non-analytic near Z equals 0 in the bosonic part, then this will result in a Riemann type puncture. So you get a cut. Basically, a Riemann puncture is like you have some cut, some branch cuts. So, and then we can count the dimensions. So say, and this, by the way, also explains this 1/2, because if you take two Riemann punctures, because they're like square roots, a square root squared is again a rational function, and then it behaves like a Neuburg-Schwarz puncture. So two Riemann punctures behave like a Neuburg-Schwarz puncture. So that's why the moduli space, the dimensions, it goes like number of Neuburg-Schwarz plus a half number of Riemann punctures. So it's like a Riemann puncture is like half a Neuburg, it's like a square root of a Neuburg-Schwarz puncture. Basically, that's the intuition. So that's the geometric setting or algebra geometric setting that we are dealing with. Now, the problem that we face is we don't really have a chain decomposition of this. We don't really know how to make a chain decomposition of this space, because we don't, because it's related to the fact that it's not geometric, it's algebra geometric. So we don't really have a boundary operator. Remember, we said that we can have a vertex in the bosonic, and then the boundary of this vertex, when all the circles were exactly equal to 2 pi, then that should glue onto some other gluing of two other vertices. And we don't really have this notion. So we don't have this boundary operator. So this whole geometric part breaks away. We don't know. We don't have this geometric PV equation, which was the top corner of our triangle. And then if I had this, I could say, okay, I have a BV equation there, so therefore I know the result in the morphism also has to be BV. So now we don't have this. So that's why we now turn this thing around. So what we're going to do is we simply integrate along this odd direction. So we pretend we also already do some integration of a part of the moduli space, because we don't know how to decompose it. And we know how to do that. But in order to show how to do that, what I need to do is I need to know a little bit about this CFD. I need to know, you see, I don't know anymore what happens here, but I do know what I can do here. So first I need to know, how does this CFD get modified? No. Works. So what I do is I replace these embedding coordinates by superfields on the Riemann surface. So they depend not just on Z, but also on Z and theta. So the phi depends on Z and theta, and the B and C also depends on Z. So I make these become not space-time, but as Riemann surface superfields on this auxiliary quantum field theory. So that, and then I can integrate over theta. So if I make these things theta dependent, I can integrate over theta, and that is the integration over the odd part of modular. And we know what it does, simply because we know what the sigma model is. We know what it does. It does essentially a supersymmetry transformation on the worldsheet. And we know how to do that, so we can just do it. And it affects what it takes our state here, and it does something to the state. It does a supersymmetry transformation on that state, which we denote by X. And it does something to the ghosts also, but that's technicalities. So we know what it does. So now what we've done is, as we said, we have no chain decomposition on the supermodular space, but we can first integrate over the odd coordinate, and then we end down on the reduced moduli space. And on this, we do have a chain decomposition. So that's what, locally, we can do it. Globally, this can go wrong, because when this super Riemann surface, when the moduli space is not split, you cannot do this globally. But luckily, in string field theory, usually we don't face this problem, because we are only talking about vertices, which are small patches in the moduli space. And there, at least at the classical level, we don't have a problem. If you add higher genus, you may have to worry about it, but we are far from being there. So the splitness for us is not an issue. So locally, we can always do this. And as I said, it effectively results in some action on these states, which I denote by X, some operator X, called the picture changing operator. So what it does, it takes our pants, and the input has to be decorated with this picture changing. And remember that the moduli space, for instance, take a 3-punctured disk, if I take an open string. It has no bosonic moduli because 3 points are always can be fixed, but it has one odd modulus. So you need to do one picture changing, which is X, pure linear. Now the thing is, the moment I put an X somewhere, I have to make sure this thing is cyclic because I want to have a field theory. So I have to put it here, here, and here just to make it cyclic. So that's fine. And then I simply define the superstring cubic vertex as being the one that I would have had in the bosonic string, except that I now have to decorate it with X. So that was really easy. Problem you face then here is that while this new Q is still a derivation of this new product, is no longer commutative. So there will be M2, it is no longer an associative algebra. You remember for the open string, we had said there is a decomposition of moduli space. We had this thing. We had this plus equal to 0, which meant that you can simply decompose the bosonic moduli space of Riemann surfaces, open Riemann surfaces is just, you can decompose it with only a cubic vertex is enough. You don't need higher vertices. So now it seems this is no longer true. But there is a trick you can use. And the trick you can use is that while this operation X is not Q exact, so it's not like a pure gauge transformation. It's not Q exact it is Q exact in a slightly bigger space. So you can actually lift your vector space with our differential. You can embed, or you can include it into a bigger space with this psi, where it becomes exact. However, this bigger space is what is called the big Hilbert space, or the large Hilbert space, in the sense that there is not really clear what is a BV structure there. So that's a longer story, but we can come to it. But in our virtually conformal field theory, there are some operators which shouldn't really, they're not really well defined, but you can nevertheless use them. And then you can embed, with the help of psi, you can embed this space here. And in this space, X is exact. So, and and using this trick, you can construct the higher order vertices. And the way more or less it goes like this, you start with the bosonic, you embed it over here, so that denoted by M2 bar. You could act simply with Q on it, then it gives an X, so that is the thing which we wanted. That is lives again over here. Or what you can do, you can take this M2, which is the one which is simply decorated by Xi, and then you can take the commutator of this M2 with this M2 here, and it gives you something like an M3, which again lives over here. But then you have to decorate it again with Xi, and then you can act on it with Q and M2, and then you get M3 and so on. So, but the story is, this is a recursive structure that works. So you could, I'll write another formula in a moment, which is perhaps more intuitive. But basically what happens is you have an L infinity, you started with Q and N2, which was a DGA, just differential graded algebra of the bosonic open string. What you can do is you can extend this to an A infinity algebra, but it's not the one you want. But you can use this auxiliary A infinity algebra together with something which is not an A infinity algebra, which is like an auxiliary object, to produce a second A infinity algebra. And this is the one you want. So basically, you could write this equation, what's written there, like this. So you could write, if you suppose you want, you write M of t as something like sum over n, t to the n, mn. So these are the end products. And then you have an equation which is d by dt, m of t. So it looks like, in fact, it's just a gauge transformation. Right? It looks like an L infinity gauge transformation, but except that the gauge parameter lives in the wrong space. It lives in a different space. The gauge parameter lives over here, whereas the object which we need needs to live over there. So this is what's called the small Hilbert space, and this is the big Hilbert space. So recursively, this can be done. And so now the result is an A infinity algebra, although you start with just a DGA, integrating out the odd directions along theta, results in an A infinity algebra, which is genuine A infinity. It's not DGA. That, however, now is consistent. Yeah. So you see, here we turned the thing around. We didn't start with something which we know and then just made a chain map. We simply said we assume or impose that the result is going to be a BV theory. And then that fixes the result. So of course, you need to use some details. What is this theta integration? But that fixes it. So you can use the A infinity structure. Imposing the infinity structure gives rise to this diagram. So use the infinity structure to actually construct the theory because you don't have the geometric analog of it. And there's an extended version of this with also a Westumino formulation under one sector by Kunitono and Okawa also. So now geometrically, what does it mean? So that is for me still a little bit unclear, to be honest, because in geometry, I don't really have this. In geometry, of course, I can say, I know what is super Riemann surface, I know what are transitions, I know how is integration, but I don't really have this trick of trivializing this integration, to write an integration as being a derivative, something like that. So I don't really have this. So I don't really know how to lift this. And I don't know what that would mean. Maybe again, if one approaches it in a smart way using good tools of algebraic geometry, maybe one could actually write this as a geometric thing. But what can at least give an interpretation of what's going on. So the interpretation is like this. So suppose you have, let me take the, this will be Z, maybe direction. So I take the real slice of C. And now what happens at this point, you do an X transformation, like an odd modulus. So you go a little bit in the theta direction. And then you have another puncture, and now there's the other puncture. So that will be then the output. And now, okay, let me denote this by dashed. Dashed would be something that has been integrated over the odd moduli. So now you have another puncture. You can combine this with, you can take this and integrate again. Or you could alternatively take this and then combine it with another puncture, because we have two punctures. We have three punctures in total, but say you come here. Maybe I'm probably not drawing this very well. So let me say I put here the second puncture. Or I take the second puncture and I identify it not with here, but with down here. And then do the odd integral. So you get something like this. It's not well drawn, but I try to do it a little bit here. I mean, again, it's maybe explicit formulas are better. You take Z, you do one integral over supermoduli space. So you add to Z a little bit of odd direction. You go like this. So then you do it again, but this insertion here, the X is not in between. Then you just get the sum. So you just shift Z by eta 1 and eta 2, which are the odd moduli, and the etas are also shifted. But now what happens if you do it the other way around? You go like this, and then you have an X at the input here. You get this extra term, so which is a shift of Z by some bosonic quantity, and this is a bosonic derivative. And this is a geometric interpretation of what's going. That's why this is not commuting. There's just two different ways of doing that, and even geometrically you can see that this is not commuting. But I don't know what is the chain decomposition of this thing, if at all. I remember, Yuji, you gave in Trieste, I think 10 years ago, you gave a talk more or less like this, but I think you never published it, no? This thing, or I was looking for where you try to understand on the modelized space perspective this. Okay. Okay. But I remember the talk.
Any operator is realized as a line
As
as a line interval. The biggest. Can it be realized as a odd modular integration?
real life, what we do is the x is realized as this at 1 over z times x, something like that. So effectively, we just inserted at the on the puncture. Effectively is inserted like this. So it's not really a current. X is not a current. That's why you have to do like this. So effectively, it's a point-like operation, but writing it like this it avoids complications with the collision of when two of these x's collide, because this gives rise to singularities. That's right. So you can take one contour, you can take another contour, would be the same. I see. Now I think I see what you're saying. That if suppose I had a chain decomposition of moduli space, then I wouldn't know what this meant. Yeah, that is probably true. In general, you could run into the boundary. That's right. So you'd have to be careful about that. That is true. Yeah. So fine. So anyway, so that is an example where you can actually use this infinity structure to construct a theory which you wouldn't perhaps know how to construct it otherwise. Okay, now I should probably hurry up. I just want to say now we've constructed, we have superstring field theory, so now we can try to do things with it. And the first thing usually, often what we do is when we have a field theory, we look at the equations of motion. So you can say, what are the solutions of the equations of motion of this superstring field theory? Again, I'm still in the open string setting with genus equals 0. So you might just ask for the Maurer-Cartan elements, solution of the equation of motion. And I've discussed a little bit at the beginning, I think in the beginning of the lecture, is that what you can ask is, suppose you have a linear solution of the linearized equation, can you extend it to a finite deformation away from just a point to extend it? And there's an obstruction theory, which is called this minimum model, which I learned, I think it's an old story, but I learned it in a nice paper by Fukaya, which is, so you can simply solve this equation perturbatively. You just invert the Q. But of course, whenever you invert the Q, you need to be careful, can you invert it? And this gives rise to obstructions. And when you can precisely not invert it when say, for instance, M2 acting with the propagator, with the inverse of Q, with the homotopy of Q, and it has sorry, again, I rewind. When the interaction vertex, the output of an interaction has a piece in the physical Hilbert space, then you cannot invert it because then Q would be 0. And these are what we call S matrices. So this is precisely the S matrix theory. So basically the statement here is that the non-vanishing S matrix is an obstruction to extending a solution away from an infinitesimal to a finite deformation. So now we want to do exactly the opposite. In perturbative string theory, that's what one does. In perturbative string theory, we compute S matrix elements. And here we want to choose our initial conditions such that the S matrices are 0. Only then we can deform away from an infinitesimal deformation into a finite deformation. So this is something that is still quite active. So and now actually quite popular again because of phenomenology. People are, I think I learned that in phenomenology, in string phenomenology, people are now a little bit tired of doing supergravity calculations. They want to do real string theory calculations. So they want to go away from just the field theory limit. So they get interested in, so for instance, what happens if you take an orbifold, which is a singular limit of a Calabi-Yau, and you blow it up into real Calabi-Yau, for instance. And that kind of calculations we can now do in principle. We're still doing perturbation theory. It's a very basic, still at the very beginning, but at least now we can start doing things, I think, which will hopefully be at some point relevant to real physics, real world physics. And I think Jing-Yang, you will talk about this a little bit, perhaps. No? So this will be the talk by Jing-Yang, which will, yes. So I will not say more about it. Just to say that we have there are applications. Now I want to say you just Shashi, just stop me when I'm over time or when you get tired of me talking. Just say stop. But so what I wanted to do is I want to do a little bit more about, can I go away from this perturbative formulation? Can I try to, now that we've seen what the L infinity does here, can we go back? Can we maybe try to close this circle and go away from L infinity? Forget about it. So is there, and because I said at the very beginning that whenever you have a BV theory and you perturb around the background, you get an A infinity structure, an L infinity structure. Can we now go back? So say, suppose you have our vertices, which I said in the first 10 minutes or so yesterday, that these vertices are just the expansion of a homological vector field, which is just the anti-bracket or the BV bracket of S with a function, which you can expand around a critical point in particular. And then these MNs are just the expansion coefficients around the critical point. So can we go away from this? Can we recover V from this perturbative expansion? So the idea one could follow is the following. You could say, suppose what we know is just the fact that we had this vertical arrow, which was this J-map or Polyakov theory, conformal field theory. It has a set of fields. Remember, we had X, B, C, and now these are the superpartner in the supersymmetric setting of B, C, beta, gamma, and psi is a superpartner of X. And they say this form, just these BRST fields, they form an associative algebra. So let's say I didn't give the basis A. So I just say it forms an associative algebra, and with a canonical bracket, simply the usual commutator. And this allows me to define a vector field by simply saying, take some string field, some psi, and some psi parameterizes a point in field space. So I have my space of fields, and then I have some point psi in it. And I can simply ask, what is the vector field acting on this psi? So V on psi is simply the Gerstenhaber bracket of the psi. So simply do like this. So now this is homological. By the Jacobi identity will be clearly homological. And this background independent, doesn't assume any background. So now I say, okay, now let me write psi. I explain it in this basis. So, and the psi A, these are the space-time fields. Remember, these are the coefficients. When I wrote down my expression for the field, I said the coefficients in front of the worldsheet fields, these are the space-time fields. So now this is something, I'm not sure what I've done here, but this should have moved. So V is a homological, so forget about this. Okay, so this should have gone up. So it just means this is a homological vector field on the space F. It's surely homological and it's a vector field, so it's fine. So what does it have to do what we want? Well, I can see, suppose V of psi is equal to 0, a critical point of this vector field. If it's equal to 0, a critical point means psi comma psi equals 0. But psi, then let psi to be of ghost number 1. then I say, oh, that's my BRST operator, because Q, Q equals 0 is the BRST condition. So whenever my BRST operator on the worldsheet squares to 0, it's a BRST operator. So it generates an odd symmetry. So I call this a non-shell condition. In the old days of string theory, this was already considered by many people, and that rather than that simply one should say a non-shell or a solution of string field theory is that whenever the BRST operator squares to 0. So that is just another way of saying that. We say psi is a field in field space, and Q is just one of the many fields. And you say if this homological vector field on Q vanishes, then on psi vanishes, we say this is a good BRST operator. So now I've chosen a background. So if this is equal to 0, then this is a background. But now I can, of course, deform. I can deform a little bit away from this psi bar. I take psi is equal to psi bar plus delta psi, and then I get the usual perturbative expansion of vertex operators. So the vertex operator is just this delta psi. So you can ask, is this a good non-perturbative definition of string theory? I don't really know, because these calculations are really complicated. And that's why probably people stopped 30 years ago to follow this route, because it was hard. But at least what we can do is we can simplify our life a little bit. Let's say, first of all, let us take the word sheet and let's collapse it to a word line, just relativistic particle. And if you get all the massive string modes, and you can run this program. And then what you find indeed that if you take the family Q of psi with depending on G, B, phi, and you demand that is nilpotent, that does indeed reproduce the supergravity equations of motion, like for the Neumann-Schwarz, for the Gramond, and not for the Ramond, for the Neumann-Schwarz fields. Ramond fields a little bit different story. So in this limited setting, it works. So this is a proposal that how to go away from this perturbative limit. We simply say the worldsheet theory gave us a basis, gave us an associative algebra. On an associative algebra, I always have a bracket. I always have a Chevalier eigenvector differential. And that is a good candidate for a homological vector field. And the BRST operators of a given worldsheet theory are just the critical points of this homological vector field. So that is a proposal. It is, of course, has its limitations, because it assumes, again, that this algebra is stable somehow. You don't create new, that the algebra doesn't change. And I don't know whether that's true. Again, you have one vacuum in string theory and another one which is far away, not continuously connected. Maybe the algebra BRST operators in that theory is very, very different. So it's again a local statement. I think it's at best a local background independent formulation. But we've recovered the V. So these VNs, they just are now the expansions of this homological vector field around the critical point. So we've been able to go away a little bit from try to come back to actually, we weren't able to construct the BV action, but at least the homological vector field, or propose rather, that would have originated from this action. So finally, then I'm already going over time, so let me do one last thing, is connection of homotopy algebras with background independent string field theory. So that's another way. Background independent string field theory is another way of trying to get away from L-infinity algebras and go back to it. Now, interestingly, there was, I think, in Kyoto's string field theory conference, perhaps 2006 or 2003, I don't remember, there was a talk by Kugo-san, where it was a review on string field theories. And he gave a very nice review, by the way, on string field theory. It was very interesting. And then, among other things, he mentioned boundary string field theory. And I remember him, then he said, boundary string field theory is not quite clear how it fits into this family of string field theory, how related. And of course, whenever you hear such a sentence, by somebody like Kugo-san, then you take it serious. You say, well, you know, probably is right, but let's challenge it. So that's, for me, it's always been a good recipe for research is whenever something seems is impossible, that's when you should try to do it. So, so now let's see. Yeah. So how does it fit? So let me just give, so boundary string field theory, let me say quickly what it is. It's an open string field theory, which was proposed by Witten in 92 and then corrected by Chatashvili short after. So the idea is you have a disk and you have a conformal filter in the bulk. So everything is conformal, but you have boundary conditions which are not compatible with conformal symmetry. So we call it a boundary conformal filter because the boundary is not conformal, so it's off-shell a priori. And furthermore, you don't assume it's a small deformation of Dirichlet boundary condition or Neumann boundary. It's just it's whatever it is. It's free, completely free. So in that sense, background independent. You're not assuming a background. So you say the boundary conditions are free, and the theory should tell you what they should be by conformal or by on-shell condition. And there is an action on this space of field theories where the bulk is always conformal, but the boundary is not, and is written like this. So O, it looks like a theta here, but should be an O, would be an operator that you can insert on the boundary. So what you do is you take V here, I write as B minus 1B. So remember this B goes from the sigma model. Never mind, the details are not important for this. But you take a certain background, you perturb it by some field. And you don't say what it is, any field. You have it's not small, it's not big, it's whatever it is. And then there is a relation between this V and this O, which is just by this B ghost. So now you say that the exterior derivative of this action is given by the inner product. You have some inner product, which we explained before, of dO, so the variation of O, with this Q, where Q is the BRST operator of this bulk theory, together with nu e to the nu. So that's the definition. It is a BV action. Witten showed it's BV. Fine. It's certainly a BV theory. So now the problem is when you actually try to evaluate this thing. You said this thing is BV, but ill-defined. The problem is it's ill-defined because, look, you now have this Q, which is some contour integral. And then you have all these integrals, and they can collide. All these points can collide to get collision singularities. This is what the Chatashvili fixed. And then you don't know a priori, what should I do? You have to regularize in a way. Now you find some regulator, you do some cutoff regularization. So this is conformal. This is really conformal perturbation theory. It's no more than that. And you try to make sense out of this. And what you do is you say you would first rewrite this action. You say, remember, we said this looks like S, comma. We said that S, comma is a homological vector field. And we took this to be, so S on nu is V on nu. And then we take this to be, if I take this to be S0, then this would be just Q on nu. That's just the BRST operator. But of course, S0, which would just be a free action. Now we say we give up this condition on being free. Then we say whatever is written here is the homological vector field. And let's compute this homological vector. Can we try to do it? We couldn't really do it, but we could do it when we assume that all these, the insertions here are on shell. So, and then you can compute the expansion of this vector field. And it turns out that the expansion of this vector field are precisely the S matrices of perturbative string theory, of Zwiebach type open string theory. So, in other words, the claim is the boundary string field theory. I can now, maybe complete this sentence of 20 years ago. Boundary string field theory computes the minimal model of cubic string field theory. So that's perhaps how it fits into this picture. So the cubic string field theory has an A infinity algebra, comes with it. And the minimal model is an A infinity algebra, which is the minimal A infinity algebra, which is given here. And last year, I think, Juro, you found the cohomomorphisms, which actually maps the two theories, which are a beautiful paper, where actually this is now, I think, fairly well understood. No? So now, finally, I think using this, again, formalism of homotopy algebras, we are able to bring this exotic boundary string field theory into the family of string field theory. So now it is also part of the family. Okay, I should stop. And let me stop here. And so what I was trying to do is just to say that homotopy algebra has been very useful in string field theory, to construct string field theory, to understand better string field theories. And it's not really, hopefully I was able to convey, it's not that exotic. Right? It's really, once you can bring it down to algebra, it's really quite manageable. So I can encourage everybody to have a go at it. So thank you very much.
Thank you very much.